Today I'll be talking about how we can understand transit users' information-seeking behavior with the use of trip planning data. So everyone's goal here is to improve public transit and encourage a modal shift away from private vehicles. One way agencies are doing this is by investing more in the provision of public transportation information services as a way to enhance travelers' experience. With the advancement of technology, this has also resulted in the development of new information sources such as social media and smartphone apps, changing the role information provision plays in travel. Previous studies that have investigated people's information-seeking behavior have done so using data collected from surveys. However, the downside is that these studies are often cross-sectional and there may be response biases. Furthermore, it's challenging to have survey data available for unplanned events such as disruptions, and conducting these surveys is costly. Therefore, this research aims to use trip search records from a mobile trip planning app known as Transit to address these questions. So the geographics, the area of the study is Calgary. Calgary Transit has the 4th highest ridership levels in Canada, and its network consists of bus routes and an LRT system shown in the blue and red lines. The data used in the study covers the time period between September 3rd, 2018 to March 2nd, 2019. And as previously mentioned, during this time period, Calgary Transit underwent a major network overhaul where 3 new bus rapid transit lines were introduced, shown as the teal, orange, and purple lines, and several route changes were made. Therefore, this also provided us with the opportunity to see how drastic changes in the network influence people's need for information. So the data used in this study came from the trip planning feature of Transit app. Each record in this data set contained a user ID, a timestamp of when a trip query was made, and latitude and longitude coordinates of the trip origin and destination. The graph on the left shows the number of trip searches made during this time period, and we see that app usage tends to dip during weekends. We also see that there is a significant reduction in searches during the winter holiday period, and this spike that we see here occurred on November 19th, which corresponds to the implementation of the new BRT system. The graph on the left shows the number of trip searches made during the histogram on the right shows the frequency of trip searches made by each user. So we see that while most people are infrequent users and do not make trip searches often, there is a sizable number of people who are more reliant on the app. We also looked at the temporal variation of trip searches and noticed that it exhibited a similar pattern to transit demand with 2 peaks that correspond to the AM and PM peak period. However, the PM peak is higher and more spread out. And we see that there are larger amounts of midday trips compared to what you would expect from actual demand. The average number of trips is also significantly lower on weekends, and it has a different pattern. The map on the right visualizes the origin and destinations of the trip searches. And we see that while the origin locations of trips seem to be pretty well distributed across the city, the destinations are mainly concentrated in 3 spots, and they correspond to the downtown core, the University of Calgary, and Mount Royal University. This might indicate that the app is popular amongst students. So we used an unsupervised learning approach to discover additional information in the data. K-means clustering algorithm was applied to each trip record using the average hourly temperature and precipitation at the time of a trip lookup, the distance of the starting location to either an LRT or a BRT stop, and the number of transfers the trip required, and finally the travel time and length of a trip. The last 3 variables were estimated by running the trip records through Open Trip Planner and using GTFS data. In the end, we ended up with 6 different clusters, and this plot here shows the differences between each cluster based on the variables. Note that these are normalized values, and the bars represent the averages within each of the groups. So some interesting things to note is that more complex trips, which we represent by having a higher number of transfers, a longer travel time and a greater travel distance make up for approximately 25% of all searches, and that trip searches that originated further from a rapid transit stop were only associated with shorter trips. When we looked at the temporal distribution throughout the day within each cluster group, we saw that while most of the clusters exhibit typical commuting patterns with an AM and PM peak on weekdays, cluster 3 and 5 were different in that the number of trip searches continued to increase around the PM peak period before dropping off. What's interesting about this is the fact that these two clusters correspond to trip searches that were made when the weather was good, meaning that the average temperature was higher and there was little to no precipitation. This may indicate that people are more willing to make non-discretionary trips during these conditions. Lastly, we looked at the spatial distribution of trip searches OD pairs. So while clusters 2 to 6 all showed very similar patterns, cluster 1, which consisted of trip searches that originated further away from a rapid transit stop, exhibit a very different pattern, and you see that the north side is significantly there's more activity compared to the south side. To investigate what factors may affect the use of transit app, a panel regression model was estimated. So in a panel data model, we have repeated observations of a group over a longer time period. The number of hourly trip searches originating in a traffic analysis zone was used as the dependent variable in our model, and below is an example of what the data structure looked like. So we had 1,296 different TAZs and 4,321 time steps to represent each hour of our time period. Then additional data sources were merged to create and test for variables in our model. So we chose to estimate a fixed effects post-long regression model because our dependent variable was account data, and we wanted to control for any unobservable differences between the TAZs. Since the number of trip searches was expected to be proportional to actual transit demand, we used the log of hourly APC within a TAZ as an offset variable to model the counts as a rate, and therefore its parameter was constrained to 1. When it comes to interpreting the model, we'll focus on the significance and effect sizes of the variables. The effect sizes can be interpreted as the % change in mean trip searches given a unit change in the independent variable, with all else being equal. So firstly, we looked at how reliability affected the number of trip searches. To measure this, we calculated the average on-time performance, which we defined as being within 1 minute early or 5 minutes late, of vehicles within a TAZ over a given time period using the APC data. Based on this result, we see that when the on-time performance is low, you can expect a higher number of trip searches being made. Interestingly, we also see that the number of active transit stops operating within a TAZ does not have a large effect on the number of trip searches. With regards to the weather condition, we see that while temperature does not have a large effect, precipitation does. In this case, we see that for every millimeter increase in precipitation, we can expect trip searches to increase by 28.7%. And this could be for 2 reasons. Firstly, people want to time their trips better to avoid having to wait in the rain or snow. And secondly, rain and snow both can cause unexpected delays to a trip. In our model, we also placed a dummy variable to distinguish between before and after the network overhaul. We see that the introduction of the new max BRT line produced a 43.7% increase on trip searches. This makes intuitive sense because routes underwent drastic changes, and it's likely that there was confusion on how to navigate through the new network. So people sought out trip planners more frequently. We also wanted to investigate the effects of transit disruption. Unfortunately, we did not have any data delay logs for this period, so we used past Twitter tweets to best identify the locations and times of severe LRT disruptions. And here we see that the occurrence of a service disruption has a very high effect on the number of trip searches made. It's expected that people would seek information, particularly using a trip planning app during these times, because travelers want to find alternative routes to reach their destination. We also included additional binary indicators to see how people's trip planning usage is impacted by time and day. So firstly, we have indicators to compare holiday and weekend usage to weekday. While there is no significant difference between weekend and weekday app usage, we see a 13% increase on holidays. This could be due to the fact that people are more likely to make unfamiliar trips on holidays, and also because transit service differs on holidays. We also looked at people's information-seeking behavior changes throughout the day by including different time periods. So the reference time used here is the AM crown period, which is defined as 7 to 8 a.m. Interestingly, we see that more trip switches were made during midday and in the PM and evening period compared to the AM peak. So a possible explanation for this is that people may be taking more non-discretionary and unfamiliar trips during midday and after work before heading home, and therefore will need to consult with trip planners more. So this result suggests that people are more likely to use trip planning tools for unfamiliar and complex trips. This is important because providing information for these types of trips can really enhance people's experiences with transit. In particular, studies found that soft factors such as the ease of navigating through a system is actually more important to people who are unfamiliar with transit. It's also very evident that people seek out information during times of uncertainty. This was seen in the model as reliability, the occurrence of service disruptions, and a drastic change in the network all had a very large effect on the number of trip searches made. So based on this finding, we really want to emphasize the importance for agencies to communicate to travelers during a disruption. This includes providing information for multiple channels, such as in-vehicle announcements, on social media, and on official websites, because not every traveler will be consulting with trip planning apps. Lastly, one possible future application of trip planning data is to use it to help agencies identify where there's a demand for transit or a desire for transit. During the study, it was interesting to know that there were instances where trip searches were greater than APC or trip searches made in an area far away from any transit services. So that concludes my presentation, and I would just like to thank Calgary Transit and Transit App for their support in this study and providing the necessary data. I'll be happy to take any questions.